Welcome to the second episode of our series, The Mother Earth. In episode 1, we learnt how enigmatic were the contrasting compositions and densities of the terrestrial and Jovian planets, the luminosity and the high internal temperature of the Sun, and the limited nucleosynthesis reactions noted within the Sun. With further advancements in the field of spectroscopy, astronomers could detect the spectral signatures of distant stars many light years away from the Sun. In 1920, Arthur Eddington, an English astronomer, raised the possibility that perhaps all the elements familiar to us also originated through nucleosynthesis reactions in the near core regions of stars more massive than the Sun. This proposition was supported by Hans Bethe in his Nobel lecture of 1939, and the stellar nucleosynthesis of elements was further elucidated by Fred Hoyle during the years 1946 and 1954. The Fraunhofer lines for hydrogen and helium, marked so prominently in the Sun spectra, were also detected in the spectra of most stars. In addition, their spectra displayed the presence of different proportions of many other elements discovered already in the 19th century from the Earth materials. Thus, the origin of chemical elements came in sight. This discovery provoked further explicit observations about the stellar interiors, and it was noticed that the stars show considerable dissimilarity in their luminosity. We all know that the luminosity was related to the star's mass and its internal temperature. The temperature achieved in the core determined the kind of heavy elements that could be generated through nucleosynthesis. The difference in the stellar mass and the core size was discernible also from the different speeds of their spin and from the time taken by them in their journeys around the centers of the galaxies to which they belonged. Stars with different masses do have a luminosity limit also. It is referred to as the Eddington limit. The Eddington limit could be linked not only to the internal temperature, but also to the degree of mass concentration towards the stellar cores. In stars with similar mass, their core size becomes the measure of the degree of mass concentration towards the core. Higher the mass concentration, shorter would be the effective radius r of the star, and faster would be its spin. The moment of inertia or the rotational inertia is given by the expression I is equal to z summation of mass r square. So, I is directly proportional to the square of the core size extending from the center. Z is a constant and m represents the total mass of each heavy element that got moved towards the stellar core due to gravity. Thus, the difference in speeds of rotation indicate the difference in the degree of mass concentration in stars. The stellar mass is customarily assessed in proportion to the sun's mass, that is 1.989 into 10 to the power 30 kg. It is because the internal temperature and composition of the sun could be used as a scale to estimate the inner temperature and composition of any star. Assuming the sun's mass as unity, the stars are categorized as low mass stars, intermediate mass stars, and massive stars. These approximate the three kinds known as red hot, yellow white hot, and blue hot stars. The blue hot stars or the massive stars contain the highest core temperatures, and in them elements with higher mass numbers are generated in maximum proportion. Only such stars, when achieving core temperatures about 10 to the power 10 degrees centigrade, could generate elements like silicon with mass number 28 up to elements with mass number around 56, that is chromium, cobalt, iron, manganese, and nickel. These elements are the neighboring elements to Fe with mass numbers varying from 51 to 58. We can comprehend why the red-orange bright sun, which has more than 99% of the mass of the solar system, is so poor in its elemental composition. But it was soon discovered that the mass numbers 51 to 58 for elements like chromium, cobalt, iron, manganese, and nickel defined a kind of limit for nuclei of elements generated in massive stars. The stellar spectra of outer layers of massive stars display mostly elements with mass number less than 56. Elements approaching mass number 51 to 58 crowd towards their cores. This limit of mass number for FeNi was soon found to be connected to the binding energy of the protons and neutrons constituting the nuclei of elements. In progressive nucleosynthesis, the binding energy refers to the kinetic energy that is required to decompose the nuclei of an element with lower mass number into its constituent protons and neutrons. Huge energy release accompanies this nuclear dissociation, but it is again consumed in creating the nucleus of the next element of higher mass number. The most stable amongst these are the nuclei with even number of protons and even number of neutrons. As a consequence, elements with even mass numbers that are divisible by the digit 4 are the most abundant. Elements may occupy adjacent positions in the periodic table, but they may not be equally abundant. In fact, elements with odd mass numbers are distinctly less abundant. As the nuclear structure of successive heavier elements gets more and more complex, higher and higher binding energy is needed at successive stages of producing nuclei of elements with higher mass number. reaching up to the production of nuclei of elements chromium, cobalt, manganese, iron, and nickel, the elements neighboring Fe in the periodic table, involves the fusion of nuclei like silicon with mass number 28, which has very high binding energy. Reaching up to this stage of nucleosynthesis, the massive stars consume nearly all the available nuclear fuel, that is, the elements hydrogen and helium. This condition precludes the further fusion of iron 56 nuclei, requiring much greater heat energy. Elements with still higher mass number are produced only if some external energy source could be drawn into the stellar system. Thus, the low mass stars and the nucleosynthesis in them take the longest time of about 10 billion years to reach this limiting stage of producing elements with mass numbers 51 to 58. The massive stars that have already reached that limiting stage have a shorter lifetime of a few million years left. Eventually, when the nuclear fuel gets exhausted, the star undergoes a colossal gravity collapse towards its core. Bouncing back, the huge and heavy mass sends very strong shock waves in the entire body of the star. The violent and recurring turbulence causes imbalance in its gyration, making it eventually unstable. The star finally explodes and dies, blowing out enormous expanse of clouds loaded with the elements it generated within it, accompanied with low amounts of elements with mass numbers higher than 56, 58. Thus, an exploding star expelling enormous light and heat in space forms the supernova. The clouds blown out in the supernova explosion mingle with the extensively present primordial hydrogen and helium in the galaxies, and together they condense eventually to form another generation of a star or stars with planets. The supernova explosion and the stellar nucleosynthesis elucidated in this episode were path-breaking discoveries of the last 2 centuries. As a corollary, we learned that not all the stars in the sky are the first generation stars that condensed from the clouds dispersed in that primordial momentous explosion in space known as the Big Bang. Many of them, like the Sun, are second or third generation stars formed through supernova explosions. This episode provides a firm thermonuclear evidence not only for the cosmic origin of elements in the universe, but also for those elements present in the solar system. The solar system has had an explosive history, condensed out of the clouds blown out of the supernova explosion of a very massive star. Space explorers are already focusing a few exoplanets with hard crusts. But so far, no other solar system with an Earth-like planet with water and breathable atmosphere has been reported from the Milky Way. In the next episode, we'll look more closely to the elemental composition of the solar system and the compositional constraints it has had since it owes its origin directly through a supernova explosion in space. Thank you.